Welcome to lecture 18. This is week 4 and we are talking about basic concepts of optimization part 2. Under this, we are talking about optimality condition of constraint optimization problems. So, in our previous lectures, we have talked about optimality conditions for equality constant optimization problem. So, today we will start our discussion on general nonlinear programming problem. So, we will first talk about optimization problems with only inequality constants, and then we will go to optimization problems where we have both inequality and equality constants. So, first we will give a brief introduction to general nonlinear programming problems. We will define certain terms such as active constants, inactive constants, regular points, and then we will discuss optimality conditions for inequality constraint optimization problems. So, this is how we will express a general nonlinear programming problem. The objective function f x is the function of n variables. So, x is n vector, it has components x 1, x 2 up to x n. This objective function has constraints of equality type and inequality type. So, there are j equal to 1 to p, that means p inequality constants of less or equal to type, and k goes from 1 to m, that means m equality constants as h equal to 0. So, minimization f x subject to g j x equal to 0, j goes to 1 to p, and h k x equal to 0, k goes to 1 to m. So, this can also be written compactly in vector notation, where we understand that x is n vector, g is a constant vector where you have p components, that means there are p inequality constants of less or equal to type, and there are m equality constants. Note, if the problem is a maximization problem, we can convert it to minimization problem simply by taking minus sign of the objective function. Similarly, if the inequality constraint is of greater or equal to type, we can also convert it to less or equal to type by multiplying both sides by minus 1. Now, look at this diagram. This represents contours of the objective function, and this region is obtained by the inequality constant g less or equal to 0. In the absence of equality constant, we will find the optimal solution to the problem within this feasible region, but we have equality constant as h x equal to 0, which is indicated by the curve, this bold curve. So, within this region indicated by the inequality constant, and then on this curved line indicated by this equality constant, we need to find the optimal solution of this general nonlinear programming problem. Note that this is shown by a single inequality constant and single equality constants, but in general you will have p number of inequality constants and m number of equality constants. So, next let us talk about what do you mean by active constants and inactive constants. An inequality constant can be of active constants and inactive constants. And inequality constants g less or equal to 0 is said to be active at a feasible point x star if the constant is satisfied as g I x star equal to 0. So, I have a constraint, say g I x is equal to 0, I equal to 1 to p. So, think about any particular constants, say g 1 x is less or equal to 0. So, if g 1 x is less than 0, the constant is satisfied. If g 1 x is equal to 0, then also the constant is satisfied. So, when the constant is satisfied at g 1 x equal to 0, we say that this is an active constant or binding constant. So, this is active constant or binding constant, or the constant is satisfied as active constant or binding constant. If the constant is satisfied as less than 0, we call it inactive constant or non-binding constant. So, by definition, an equality constant is always active at any feasible point. The constants active at a feasible point x star restrict the domain of feasibility in the neighborhoods of x star, while the inactive constants have no influence in the neighborhoods of x star. Look at the diagram. Consider the point x star. The constant g 1 equal to 0 satisfies, or x star satisfies g 1 x equal to 0. So, g 1 is active constant. The feasible region is the domain obtained by g 1, g 2 and g 3. X star belongs to this feasible region. So, all g 1, g 2 and g 3 satisfies, x 1 x star is satisfied by all g 1, g 2 and g 3, but only g 1 is active because it is being satisfied as g 1 equal to 0, whereas g 2, g 3 are inactive constants. They are not satisfied as g 2 equal to 0 or g 3 equal to 0. Next, we will introduce another important definition known as regular points. So, consider first an equality constant optimization problem, minimization of f x subject to h x equal to 0. A point x star satisfying the constant h x star equal to 0 is said to be a regular point of the feasible set if f x star is differentiable and gradient vectors of all constants at the point x star are linearly independent. So, first regular point is a feasible point, and at regular point the gradient of all vectors, the gradient vectors of all constants are linearly independent. So, try to understand the definition of the regular points. A point x star satisfying the constants h x star equal to 0 is said to be a regular point of the feasible set if f of x star is differentiable and gradient vectors of all constants at the point x star are linearly independent. So, the regular point is a feasible point where the gradient vectors of all constants are linearly independent. So, what does linear independence mean? The linear independence means that no two gradients are parallel to each other and no gradient can be expressed as linear combination of others. Now, let us consider that with this equality constant I also have inequality constant. So, when inequality constants are also present, then for a point to be regular, the gradients of all the active constants including inequalities must also be linearly independent. So, for a general problem where you have both equality and inequality constants, the regular point is a feasible point where the gradient vectors of all active constants are linearly independent. All active constants means all equality constants as well as all inequality constants that are satisfied as equality type. That means all inequality constants that are active. So, for a general nonlinear programming problem where you have both equality and inequality type constants, a regular point will be a feasible point where the gradients of all the constants or gradients of all the active constants are linearly independent. So, we have talked about Lagrange multiplier methods for equality constant optimization problems in previous lecture. So, let us now formally put the theorem for Lagrange multiplier methods. So, let us consider the minimization of f x subject to h x equal to 0. Assume x star is a regular point of h x equal to 0 and let x star be a local extremum of the objective function f subject to h x equal to 0. So, all we are saying that let x star be a regular point of the optimization problem that we have described. Then there exist m unique Lagrange multipliers such that gradient L equal to gradient f plus lambda transpose gradient h equal to 0 evaluated at x star. That x star is the regular point which is likely to be local minimum or maximum, that is local extremum. This can also be written equivalently as in the sigma notation as del L del xi equal to del f del xi plus sigma j equal to 1 to m lambda j del h j del xi I equal to 1 to m, that means derivative of equality constant h with respect to all decision variables x I equal to 1 to n. And next you take the derivative of Lagrangian function with respect to Lagrange multiplier and you get back the equality constant. So, this is the theorem which says that if x star is a regular point, then if x star has to be local extremum of f subject to the equality constant h equal to 0, then there will exist m unique Lagrange multiplier which will satisfy gradient of L equal to gradient of f plus lambda transpose gradient of h equal to 0 at point x equal to x star. Now, let us introduce inequality constants and let us see how we use Lagrange multipliers to find out necessary conditions for optimality for optimization problems with only inequality constants. So, let us consider a problem minimize f x where x is n vector subject to p inequality constants as g j less equal to 0, j equal to 1 to p. Note that we are using the inequality of less or equal to type. So, the value of g, the constant function, can be 0 or negative. As we discussed before, if you have an inequality constraint which is greater or equal to type, you can always convert it to less or equal to type by multiplying it with -1. We can convert such a constant to an equality constant by adding a slack variable, and this slack variable must be greater or equal to 0. How? You have, let us say I have inequality constant as g x less or equal to 0. So, I can always add a positive term such that the right hand side will be equal to 0. G is less or equal to 0. So, you have to add a positive term so that right hand side equal to 0. In fact, you can add a 0 term also if g is equal to 0. So, the restriction on sigma square is that it should be greater or equal to 0. So, in beta terms I should say that I can always add a non-negative term to g x so that the right hand side will be equal to 0. So, I can do this for all inequality constants. So, all inequality constants, say p inequality constants, can be converted to p equality constants by adding a slack variable which is non-negative, that means greater or equal to 0 type slack variables. And these slack variables must be found out as a part of optimization problem. So, g j less or equal to 0 can be converted to g j plus sigma j square equal to 0. So, if sigma square equal to 0, it means g equal to 0, you do not need any slack variable to make the right hand side equal to 0. So, g equal to 0 means the constant is satisfied as active constant. So, it is tight constant, there is no slack. If sigma square is greater than 0, that means g is less than 0 and you need a greater than 0 quantity to make the right hand side 0. So, if sigma square is greater than 0, g is less than 0, so the constant is satisfied as inactive constant. So, now let us see how we make use of this to write down the optimality conditions for optimization problem with inequality constants. So, I have an optimization problem, n variable objective function and p inequality constants all less or equal to type. So, I can convert it to an optimization problem with p equality constants by adding p non-negative slack variables. I represent them as sigma j square. So, if we have p constants, inequality type constants, you need to add p non-negative slack variables. So, this problem has now been converted to equality constant optimization problem. Now, I can make use of the Lagrangian method that we have learned for equality constant optimization problem. So, let us first define the Lagrangian. So, the Lagrangian can be defined by defining a Lagrange multiplier for each equality constant, take their product, sum them up and add the sum to the objective function. So, the Lagrangian function is defined. Now, if x star is a regular point, then the first order necessary conditions for x star being an extremum can be obtained by setting the gradient of L to 0. So, you can take the gradient of L with respect to x, that means decision variables, set that equal to 0. You take the derivative of the Lagrangian L with respect to Lagrange multipliers, set that equal to 0, and then we can also take the derivative of the Lagrangian function with respect to the slack variable and set that equal to 0. So, we need to solve these equations and then we will find out the stationary points, which is a candidate for minimum. So, let us see what we get as necessary conditions for optimality. So, this is the Lagrangian function that we defined in the previous slide. So, if x star is the regular point, that is the local minimum of f x, then the necessary conditions are you first take the gradient. So, look at this first. So, this is nothing but the derivative of the Lagrangian with respect to each decision variables I equal to 1 to n. So, set that equal to 0. Next, you again take the derivative of the Lagrangian function with respect to Lagrange multiplier. And set that equal to 0. So, when you take the derivative with respect to Lagrangian multiplier lambda j, you see what you get back is g j x plus sigma j square equal to 0. And of course, sigma j square is greater or equal to 0, that non-negative condition on the slack variables. So, apart from these, you also have to take the derivative of the Lagrangian with respect to the slack variables sigma. So, if you do that, note here you will get del L del sigma j equal to 2 lambda j sigma j equal to 0. So, this is known as switching condition. Note here either lambda j will be equal to 0 or sigma j will be equal to 0. And then a non-negativity condition or restriction on the Lagrange multipliers lambda. All lambda must be greater or equal to 0 for a minimization problem with less or equal to type inequality constants. So, Lagrangian multipliers for g less or equal to 0 type inequality constants are all non-negative. So, they lambda j's may be greater than 0 or lambda j may be equal to 0. So, if g j less than 0, the lambda j equal to 0, meaning if the constant is satisfied as inactive constant, the corresponding Lagrange multiplier may be 0. If g j equal to 0, the lambda j may be greater or equal to 0, meaning if the inequality constant is satisfied as active constant, the corresponding Lagrange multiplier may be greater or equal to 0. So, let us try to understand this non-negativity restrictions on the Lagrange multiplier. For a minimization problem, if the inequality constants are of less or equal to type, then the corresponding Lagrange multiplier are non-negative. So, lambda greater or equal to 0. So, let us try to understand this. Let x star be local minimum, constants are of less or equal to 0 type. So, let us consider the first order perturbations for the objective function f and the constant g at the local minimum for feasible non-zero perturbation. Remember, feasible non-zero perturbation. So, I can expand the function f x by Taylor series as shown. So, f x minus f x star equal to d f dx into delta x. Delta x is x minus x star, a perturbation or deviation. So, if the function has minimum at x star, so f x minus f x star will be greater or equal to 0. So, this allows me to write that df dx into delta x at x equal to x star is greater or equal to 0. Similarly, if I have constants, inequality constants of g less or equal to 0 and the feasible perturbation will mean that dg dx delta x is also less or equal to 0. So, df dx delta x greater or equal to 0, dg dx delta x less or equal to 0. Now, look at the necessary conditions for optimality. Del f del x plus lambda del g del x equal to 0. Now, del f del x is greater or equal to 0, whereas del g del x is less or equal to 0. So, lambda has to be greater or equal to 0. So, this is true when I have a minimization problem and the inequality constants are g less or equal to 0 type. If I have a minimization problem where the constants are of the g greater or equal to 0 type, then the Lagrange multiplier must be non-positive. That means, Lagrange multiplier must be less or equal to 0. You can always analyze this by considering this. You can also analyze this as follows. Look at the Lagrangian function. If lambda I are greater or equal to 0, this will ensure that this Lagrangian function has a well defined minimum. If lambda I are allowed to be taken negative values, then because of this lambda I sigma squared term, you can make the Lagrangian function L smaller and smaller. So, for the minimization problem, we have to take non-negative or lambda greater or equal to 0. Similarly, if you have a problem, minimization problem with g I x greater or equal to 0 type inequality constants, then note that this will be minus to make the right hand side 0 here. So, in that case, making lambda I positive will make L or the Lagrangian function smaller and smaller, again due to presence of this term. So, this way you will be able to analyze the restrictions on the Lagrange multipliers. So, remember, we are expressing the problem as minimization problem and the inequality constant as less or equal to type. So, the Lagrange multipliers are all greater or equal to 0 for the inequality constants. So, now I can express the optimal conditions, necessary conditions for optimality in an alternate form. Note, this was my Lagrangian function. So, this is the gradient of the Lagrangian with respect to the each decision variable, which must be equal to 0. This represents the derivative of the Lagrangian function with respect to Lagrange multiplier, which will be equal to 0, and this derivative gives you g plus sigma square equal to 0, and the restriction on sigma square is that it has to be greater or equal to 0, and that is why we take sigma square instead of sigma. Now, note that these two can be combined by g is less or equal to 0 constraint, because these two constraints, this constraint and this constraint, basically ensures g less or equal to 0. So, if I can directly ensure g less or equal to 0, which I call feasibility condition, I do not need these two conditions, and I can do away with the sigma term. Similarly, the gradient or the derivative of Lagrangian function with respect to the slack variable sigma gives me 2 lambda j sigma j equal to 0, which we call switching function. Now, if sigma j equal to 0, if sigma j equal to 0, lambda j need not be 0. If sigma j equal to 0, it means the constant is active. So, g equal to 0, and if sigma j is not 0, it means that the constant is satisfied as inactive. So, g is not equal to 0, in that case lambda equal to 0. So, this constraint 2 lambda j sigma j equal to 0 can be replaced by lambda j g j equal to 0, where for active constant, that means g equal to 0, lambda will be greater or equal to 0, and for inactive constant g less than 0, the lambda will be equal to 0. So, this is how I can represent an alternative form of the necessary conditions. So, if I just summarize, the Lagrangian is obtained and the necessary conditions are obtained as the gradient condition, which is the derivative of the Lagrangian with respect to each of the n decision variables, which will be equal to 0. Then the feasibility condition, that means inequality constants g less or equal to 0. So, this has to be satisfied, inequality constants has to be satisfied for all p inequality, we call it feasibility condition. Then lambda j g j equal to 0, for you have p inequality constants. So, you will have p Lagrange multipliers. So, the product of the Lagrange multiplier and its so product of the inequality constants and the associated Lagrange multiplier will be equal to 0. So, lambda j g j equal to 0 for j equal to 1 to p, this is known as switching condition. It represents either lambda j equal to 0 or g j equal to 0. G j equal to 0 for active constants, g j is not equal to 0 for inactive constants, and lambda j is greater or equal to 0, which represents non-negativity condition. So, this represents the alternative form of the optimality conditions or the necessary conditions for optimality for optimization problem with inequality constants. Solutions of these equations will lead to the stationary point, which is a candidate for minimum. So, with this we stop lecture 18 here.